Welcome everyone to the High Performance Fundamentals YouTube channel. I'm Lawrence Snyder and I certainly appreciate you tuning into the channel today. Okay, so today's video is intended to be a more advanced, next level discussion about battery performance characteristics. I'll be covering a variety of lesser known but equally important battery performance ratings and specifications. Okay, so before we get started, if you'd take a moment to subscribe to the channel and click the like button, I certainly would appreciate it. Thank you for that. Okay, so let's get into it. Battery performance ratings. Your basic or general ratings, I've made a video about this and you can refer back to that video if you would like to. And I get into great detail about what these general or basic ratings and specifications are. And they are important and they're what you're most familiar with when shopping for a battery, what's actually going to be printed on the battery label or in the catalog, and what you normally would use to make a decision when selecting one battery or another. Now that is the same battery chemistry, whether it's a lead acid battery, but let's say you want to change chemistries and you want it to be a lithium based battery and you want to compare them side by side. There's more to know, there's more you're going to need to know to make an informed and accurate decision. So let's move on to your next level or a more advanced rating or set of ratings and specifications. And that would be the battery C rate, its energy density rating, its power density rating, and a term called voltage sag. Voltage sag can also be known as voltage dip or voltage drop. All three of those are accurate, but voltage sag is generally what's used to describe a voltage drop situation while the battery is under a load or is being discharged. If you're monitoring battery voltage while you're discharging the battery, then you'll see a certain amount of voltage sag or voltage drop. So what I'm saying is this. So let's say that the battery's voltage, open circuit voltage, no load on the battery whatsoever, but 100% state of charge. Let's say the battery voltage you measured was 12.7, 12.8. Let's just say it's 12.8. And you begin to discharge the battery and you decide you're going to discharge it at a 20 amp rating. So it goes from 12.8 down to 12.7, whatever. So that 0.1 volt would be the voltage sag. But now let's say that you discharge the battery at a rate of 100 amps, a much greater rate. So now instead of it being 12.8, now instead of it going down to 12.7, it's dropped down to at 100 amps. Let's say it's dropped down to 12 volts or 11.9. Or 12.2, whatever it might be. So when you're comparing one battery, especially battery chemistry, to another, the amount of voltage sag or voltage drop during a specific amount of draw or amperage draw or discharge rate, they're not going to be the same. One will have a more significant voltage sag or dip or drop than another, so that's important to know, right? Okay, so let's look at our performance influencers. So what influences your ratings if you're doing a battery test, and you're trying to determine its actual rate, comparing with the manufacturer specification to your actual test procedure. Several things are going to influence the battery's performance, and when comparing one battery to another, there are certain things that are inherent to the battery that are more inherent to one battery or another. Let's say Peukert's law, for example. Peukert's law, or also known as the Peukert effect, has a much greater effect on a lead acid based battery than it does on a lithium ion based battery. So that plays a much bigger role, and that's really important to know, and one of the reasons you would choose lithium ion over lead acid. So battery chemistry is a great performance influencer. Like I said, lead acid chemistry or lithium ion based chemistries like lithium ferrophosphate or lithium iron phosphate, same thing, or lithium titanium oxide or lithium titanate, also the same thing. So you basically have three: lead acid battery, lithium titanate, and lithium ferrophosphate. But so then, of course, we're going to talk about Peukert's law. Peukert's law does have a big impact on lead acid batteries, not so much on lithium ion batteries. Then we're going to talk about the battery temperature itself. When we say temperature, we're talking about what is like the optimum temperature. In all of the various chemistries, the optimum temperature is usually in the 25 degrees Celsius, 77 degrees Fahrenheit would be like your optimum temperature. So when we're talking about a higher temperature, then we're talking about a temperature greater than 25 C or 77 degrees Fahrenheit. And we're talking about colder temperatures or lower temperatures. We're talking about temperatures less than 25 C or less than 77 degrees Fahrenheit. Now, the important thing to know here is that In most cases, if not all cases, as the battery temperature goes up, only to a certain point, like for example, if you're at 77 degrees Fahrenheit, at 200 degrees Fahrenheit, that's terrible. I mean, the battery's, that would be a terrible situation. But if you go from 77 degrees Fahrenheit, let's say you go to 100 degrees Fahrenheit, the battery's temperature of the battery performance will actually improve slightly. In most all cases, lead acid batteries and lithium ion based batteries, as the temperature goes up, there's a small performance improvement. But what you have to know is this, that as that temperature goes up, the battery tends to degrade at a faster rate. So that higher temperature, although the battery performance might be slightly greater, the battery won't live as long. So 77 degrees Fahrenheit is just optimum, is what you got to know. Okay, so as the temperature goes down, on the other hand, and I'm going to show this later, we're going to actually put some battery specifications on the board. I'm going to actually show you exactly how the temperature impacts those batteries. But what you need to know is this: as the temperature goes down, the battery's performance characteristics drop drastically. As you go from 77 down to 32 degrees Fahrenheit, which is 0 degrees Celsius, or all the way down to 0 degrees Fahrenheit, which is negative 17.8 degrees Celsius. As the temperature goes down like that, the battery's performance drops drastically, and that's important to know, right? So then from there, we get into the battery's state of charge. Whenever you're testing any battery, when you're actually going to perform tests on a battery to determine if, like, let's say, for example, the manufacturer's specifications are accurate, or where does the battery lie? Is it in good condition? Is it not in good condition? So when you're doing your state of charge, you always want to make sure the battery is at a 100% state of charge. You don't want it to be at 90 or 80. It's going to have a great impact on the battery's performance, on the actual test results. It's going to negatively impact your test results, so it needs to be at 100% state of charge. Now, with that being said, I want to bring up what's known as a surface charge. Okay, and you don't want to test it when it is first charged. What I mean is this: if you have a lead acid battery, and let's say the battery's at 100% state of charge with open circuit voltage, the cables are disconnected from the battery's not being discharged or loaded in any way, shape, or form, but it is 100% state of charge, you're going to expect to see between 12.6 and 12.8 volts, depending on the chemistry, right? The concentration of sulfuric acid on a lead acid battery is the biggest impactor on the battery voltage itself, but some are greater than others, 12.6 to 12.8, sometimes even as much as 13 volts on some of them. But what you need to know is this: when you first charge that battery and you're done with the charging process, and let's say you go through a lengthy, fully charged process where it took you 5 or 6 hours to really properly charge that battery, when you remove the battery charger from the battery, if you test the voltage at that point, you might have 13.2 volts, 13.3, 12.95. Not sure which you'll have, but it'll be greater than the actual battery 100% state of charge voltage. So that is considered a surface charge. Now, the best way to remove that surface charge and get down to the voltage where you do want to actually do your testing is to let the battery sit between 6 and 12 hours, or maybe 8 to 12 hours. Now, if you're in the business working on cars or testing batteries, whatever, in most cases, 99% of the time, you're not going to have the time to wait 6 to 12 hours for the battery voltage to stabilize or to normalize. You're not going to have time to do that. So one of the things you can do is you can put a small load on the battery for a short period of time. As an example, you can turn on your headlights, put on your high beams, let them stay on for 15 to 30 seconds, somewhere in that range, and then shut them off. That'll help to remove this surface charge that's on the battery and get you down to a more realistic state of charge, 100% state of charge voltage, which would maybe go from 13.2, get you down around 12.8, or 13.0 down to 12.7, something like that. But the downside to that is this: if the best way is to let it sit, but I realize, being in a business all my life, that you're not going to have 6 to 12 hours to wait. So the only downside to that is this: by putting the battery under a load, by discharging the battery to some extent, you have obviously reduced. It's no longer at 100% state of charge. You've taken some of that charge away from the battery. To what extent? A very, very small extent. Is the battery now at 99% state of charge, 98.5% state of charge? It's really hard to say, and it really shouldn't impact your test results in little to none. I mean, very, very little change in your test results. So it is a viable way of getting the battery down to a true 100% state of charge and to remove that surface charge. And it's not uncommon to do that. Just letting the battery sit and testing it after 6 or 8 or 10 or 12 hours is the best way to do it. But in most cases, I realize you're not going to have time to do that. So let's move on to the state of health of the battery. So when you get your battery brand new, let's say you buy a brand new lead acid battery and it comes dry. There's no electrolyte in the battery. It's just assembled empty, right? As far as electrolyte, it's empty. And they provide you with the electrolyte. This is not uncommon. And to this day, today that's not as common as it used to be. It used to be like when I was growing up, for example, you always had to add the acid or the sulfuric acid solution, the electrolyte, to the battery. You actually added it once you purchased the battery. It didn't come with the electrolyte in the battery. And today that still is a thing. I've seen some UASA, like motorcycle batteries, the AGM batteries, and some of the others that they come with the battery and the electrolyte separate. I've seen even some of the motorcycle batteries from an interstate batteries, same way. The electrolyte is separate from the battery. And my guess is that this is in the United States where I live, and some of these batteries were probably shipped from overseas, from Japan. If it's a UASA battery, maybe it came from Japan. So it wasn't shipped assembled, if you will. The electrolyte was shipped separately from the battery in the same box, but not actually, the battery's not activated, if you will. So at that point, the battery is 100% brand new. You get the battery, there's been no electrolyte put in it. It is a truly 100% fresh, brand new battery. You put the electrolyte in the battery, you top it off, you go through the charging procedure, you let it sit. At that point, your state of health is 100%. The battery's never going to be better than that. Never. And from there, as the battery ages, not just calendar life, but the amount of times that it is actually discharged and recharged, is that's called cycle life. The more and more times you do that, the state of health of the battery becomes less than 100%. It becomes 95%, 90%, 85%, 80%. Over time, it does degrade. Now, that being said, you have to take that into consideration when performing a test on a battery, so that you don't expect to see the actual ratings. For example, if your amp hour rating was 100 amp hours and you perform a test on the battery and you get 80 amp hours or 82 amp hours or something, but the battery is older, whatever, so it's basically, its state of health is probably somewhere in the 80% range. So therefore, your test value is going to be about 80% of what it was when it was new. Now, that's not abnormal. It doesn't necessarily condemn the battery. I just want you to know this. That doesn't necessarily condemn it. It just means that it's aging. So it's something to think about when you purchase a battery. If you are the type of person who is determining what battery, or you're in a situation, not necessarily the type of person, but both, the type of person and you're in a situation where you need to come up with a battery. It's not a factory replacement battery where the manufacturer of the car has already determined what the amp hour rating should be, what the cranking amp rating should be, what the reserve capacity should be. The manufacturer's already determined that, and you're just pulling it out and putting in a new one. You're just going by what they did, easy peasy, right? But let's say that you're building a car or an off-road vehicle or a boat or whatever it is you're doing, and you're trying to calculate what you need. Take this into consideration. Whatever calculation you come up with, like, okay, this is what I need, bare minimum. Make sure you build a cushion into that, because what you come up with, that result, is going to be when the battery's brand new at 100% state of health. But what about when the battery begins to age? If you don't have a cushion built in where you have more amp hour capacity than you need, more cranking amp capacity than you need, more reserve capacity than you need, then as soon as the battery state of health starts to drop, which is normal, as soon as that happens, the battery won't be able to pull the load any longer. It'll no longer be sufficient. It'll be, like I said, unable to handle the task. So you always want to make sure you build in a little bit of a cushion so that as it ages, it still is more than capable of performing its job, performing the task that you assigned to it, right? So keep that in mind. But like I said, the state of health has a big performance influencer is your state of health. Big performance influencer is your state of charge, the battery chemistry, or Peukert's law, and the temperature. All right, so now I'm going to elaborate on all of this. I'm gonna define what all of this means and make it to where you can easily understand it, and not only easily understand it, but thoroughly understand it, so that you can move forward with the knowledge to make informed, calculated, correct decisions in your battery purchase, right? Okay, so some notations that you need to know this, right? So you need to know how the battery operates. In order to understand what's going on here and to explain these performance influencers and these advanced ratings and specifications, you have to know how the battery actually performs to understand what I'm going to try to explain. So let's look at a couple different things. Let's look at the battery capacity itself. All right. So in a technical term, we're looking at a energy storage device that has both kinetic and potential energy. Okay, so let's break that down a little bit further and talk about the electrochemical reaction process. Now, this is what occurs in the battery to convert the chemicals in the battery, any electrolyte in the plates of the batteries, your positive and negative plates, your cathodes and your anodes, right? So you have chemical reactions taking place between the plates and between the electrolytic solution. The process, so to explain that further, the process of converting chemical energy into electrical energy. Now, like I said earlier about getting the battery, and you got the battery and the battery was dry, you added the electrolyte, right? And once you've added the electrolyte, that electrochemical reaction process starts to take place, right? At that point, it immediately starts to occur. And then once you actually charge the battery, and now you've charged it, it's sitting there, it's at 100% state of health, 100% state of charge. At that point, you have a lot of kinetic or stored, right, stored electrical energy at that point. Okay, now, that's not all the battery has to offer, right? Yes, you do have a total volume of stored electrical energy. There's a certain amount, okay? Now, as you discharge that battery, that process that takes place, that electrochemical reaction process, it continues to occur. So that process not only provides you with your initial stored electrical energy, it also starts to provide more available or potential electrical energy. So yes, you've got your stored electrical energy, but as you discharge that battery, that process continues, right? And as it's continuing, it's taking that chemical reaction process and producing electrical energy. As you discharge it, it continues to occur until such time that the battery becomes discharged and that process stops. Okay, so as that process occurs, basically, and I'm going to get into this in another video, much more in depth. When you recharge the battery, you reverse that process, right? So you go from a discharge state to a recharge state. So you just literally just rewind, you just reverse the process, right? But you need to understand that the battery capacity itself is a kinetic and potential energy, right, with a total volume of stored and available electrical energy. So it's a combination of the two. That is your actual battery capacity, right? And that's very important to understand the available electrical energy part of that equation or part of that definition when it comes to Peukert's law and C rate. That becomes very important. You have to understand what's going on in a battery to understand C rate and Peukert's law and how the battery chemistry affects it. So let me just go over it one more time. Battery capacity is equal to kinetic and potential energy, which broken down further means the total volume of stored and available electrical energy. That's the battery's capacity, the total volume of stored and available electrical energy. Now, internally what's happening is it's an electrochemical reaction process, the process of converting chemical energy into electrical energy. That's what's going on inside the battery, and that's the definition for battery capacity. And then from there, as we explain these things, maybe you can even rewind and we'll go back over this again, or you can go back over this again to drive this point home a little bit. But in order for me to define these in a manner in which it becomes understandable or makes good sense, then you guys to understand this, all right? So, okay, so from there, let's move on. And the next thing I'm going to get into is we're going to talk first about batteries, energy density, and power density. Then we're going to get into C ratings. Then from getting into all that C rating explanation, then we're going to get into Peukert's law. And then we're going to talk a little bit more about your electrochemical reaction process and what's known as electrochemical limitations. All right then, let's talk about a battery's energy density and a battery's power density, okay? And we can define that in two different ways. One of them is known as a gravimetric measurement, and the other one is a volumetric measurement. One of them is basically a gravimetric measurement. We're talking about the battery's physical weight, and a volumetric measurement, we're talking about the volume that it consumes, the space it takes up, right? Now, I've chosen to use gravimetric measurements as my defining terms for battery energy density and battery power density as opposed to a volumetric measurement. And the reason I did that is because in my research, in most cases, what is publicized is a gravimetric measurement. You rarely see a volumetric measurement, although you will at times see that. It's easier to find gravimetric measurements, and it's also easier for you to calculate a gravimetric measurement yourself by the physical weight of the battery, right? Anyway, so let's define battery energy density. The amount of available electrical energy or battery capacity relative to its physical weight or mass, calculated based upon the watt-hour rating and the total weight or weights of the individual cell or cells. Okay, so explain that a little bit further. If a battery is assembled, okay, and let's say it weighs, come up with a number, let's say it weighs 20 kilograms or 44 pounds. And you say, well, I believe the cells are going to be, let's say, instead of 20 kilograms, I think the battery case itself, maybe the electrical posts or terminals, the battery management system, if it has one, the cell balancer, let's say all that were to weigh, let's say it's a 20 kilogram battery, and those you figure weigh 2.5 kilograms or 5.5 pounds, something in that order. So now you have, what's left over is the weight of the cells. So now you know the weight of the cells. But you do have to kind of fudge the numbers a little bit. You have to come up with an educated guess onto what those components weigh to break it down to what just the cells weigh. But at that point you have the overall weight of all of the cells, not one individual cell. And that's what I mean when I say total weight or weights of the individual cell or cells. So that's how you would calculate it. So now you know the total, let's say the total battery capacity, or let's say amp hour rating or watt hour rating of that battery assembly. And by eliminating the weight of the case, the connectors, the terminals, the battery management system, and getting just down to the weight of this combined weight of all the cells, now since you have that weight and you have the watt hour rating, you can do the calculation. Now, if you're going to buy battery cells and you buy individual cells, which you then connect together with bus bars or cell connectors of one type or another, because the manufacturer is going to give you the weight of that cell. So now you know the weight of the cell, and they're also going to give you the actual, like I said, the watt hour rating and the weight. And they'll also will usually give you an energy density rating also, but you can calculate it because now you know they give you, it's publicized, the total weight of the cell. It's publicized the watt hour rating of that cell, or the amp hour rating and the voltage of that cell. You can calculate the watt hour rating yourself by taking voltage times amperage. So that they say let's say the cell is a nominal voltage of 3.2 volts and it's a 20 amp hour cell. So 3.2 times 20 is 64 watt hours. So now you know the watt hours and you know the weight. So you just do the calculation, just do the math. Now you know. And if you're going to use 6 cells, just take that times 6. You're going to use 4 cells, take that times 4, however many cells you're going to use, right? And now you know what the total watt hour rating is per cell and what the overall weight of all the cells will be. You have all that information. All right, so once again, like I said, so battery energy density is a gravimetric measurement. It's the amount of available electrical energy or battery capacity relative to its weight, physical weight, or mass, calculated based upon the watt hour rating and the total weight or weights of the individual cell or cells. And the calculation would be amp hour rating times voltage, which gives you your watt hours rating, divided by the mass, or watt hours per kilogram, or watt hour divided per kilogram. Watt hours per kilogram, WH over kg. So amp hour rating times voltage divided by the mass is the same thing as saying watt hours per kilogram, or watt hour divided by kilograms, or watt hours per kilogram, right? Okay, so let's move on to power density. So now we know the energy density of the battery. Now we want to calculate what is the power density of the battery. Okay, so once again, we're going to use our energy density information. So it's a gravimetric measurement of power density, the maximum rate, the rate of available electrical energy discharge relative to its weight. Okay, so calculated based upon the maximum output wattage and the total weight or weights, mass, physical mass of the individual cell or cells. So we take the maximum discharge wattage. So for example, let's say that you measure voltage sag and you measure discharge amperage. So let's say that your actual output voltage is, let's just come up with a number. Let's say your output voltage while measuring at a maximum rate of discharge is 12 volts. Let's say that maximum rate of discharge is, let's just say it's 250 amps. So we take 250 amps times the measured voltage while discharging. So we take 250 times 12. We have 3,000 watt hours. All right, so we have an amperage rating. We have a voltage rating. So now we have a wattage rating, not watt hours, I'm sorry, a wattage rating. So maximum discharge wattage divided by the mass. Maximum watts per kilogram, or watts per kilogram, not watt hours anymore, but watts per kilogram. And like I said, so let me go over that one more time. The maximum rate of available electrical energy discharge, so the maximum rate of discharge, the most we can get out of it, total. We're getting 500 amps, 550 amps, 600 amps. What's the most it'll discharge? No matter what we do, the most we can get out of that battery non-stop for a brief moment, it's going to be for a brief moment, is let's say 500 amps, 550 amps, 600 amps. Let's say it's 800 amps, but it's the maximum we can get, okay? So at that point, when we're getting that maximum amperage, we measure the actual voltage at the battery while we're discharging it. And from there, we can come up with the maximum wattage, the maximum discharge watts or wattage. And then we take that divided by the known mass, so we get maximum watts per kilogram or watts per kilogram, right? And that is a battery's power density. Okay, so things that can affect that is the battery's C rate plays a big role in that, and we're going to get into that in just a second. So the C rate is what the battery can discharge. Let's say, for example, it's a 100 amp hour battery. So can it put out 10,000 amps? You know, like a rate of 100 C. 100 times 100 is 10,000. Can it do 100 C or 10,000 amps? Okay, well, maybe it can do 6 C or 600 amps. Or maybe it can only do 2 C, 200 amps. That has a big impact on the battery's power density. So not only its amp hour rating, but also its actual C rate to determine its actual discharge rating. So energy density is one thing, but power density is a whole other thing, and it's just as important. You know, for example, you can have a battery that's extremely capable. Let's say you have a battery that's got 300 amp hours. That's great. But let's say it had a rating, a C rating of 1 C. Well, then it can only put out maximum would be 300 amps. Well, 300 amps in some cases wouldn't even turn the engine over. You know, it would power the starter motor, but it may not have enough electrical energy to actually crank the engine over, at least not initially, right? So even though it has tremendous capacity, its C rate's super low, and that would not be good as a starting battery. So you wouldn't want to use that as an SLI battery because its C rate's too low. So power density becomes very important. Your energy density obviously is very important, but so is your power density, right? So they go together, they go hand in hand. And that's where we get into your battery C rate. So what is a battery C rate? Okay, it indicates a battery's specified discharge and recharge rate relative to its capacity rating. That's what I was just saying. So if it has a 10 amp hour capacity rating, but let's say it has 100 C. So 100 C times 10 amp hours would be 1,000 amps. Well, damn, that's a lot of amperage output. Now that battery's going to discharge really rapidly because it's only a 10 amp hour battery. We're discharging it at 100 C or 1,000 amps, right? So a 10 amp hour battery at 1,000 amps is not going to last very long at all. And you can calculate that. Excuse me. So, all right, so battery C rating indicates a battery specified discharge and recharge rate relative to its capacity rating. So battery capacity rating equals 100 amp hours. That's going to be what we're going to utilize here, right? We're going to assume that for these calculations, we're talking about a 100 amp hour battery, okay? So, for example, let's say the battery is rated at 30 C. So you would take 30 times 100 amps, and you'd have 3,000 amps, and then take your 60 minutes, because we're talking about like an amp hour rating, okay? Amps per hour, let's just say. So you take 30 times your rate, would be 30 times 100, would be 3,000 amps. But you take your 60 minutes, which is an hour, but in this case you're going to divide it by 30. So now we're talking about 3,000 amp draw, but only for 2 minutes. So this 100 amp hour battery, let's say you can put out 3,000 amps at a 30 C rating, which that would be very, very rare. But let's just say that was the case. It's only going to do it for 2 minutes, right? Now, that does not take into account Peukert's law, and we're going to get into that in just a minute. This is in theory. But if the manufacturer of the battery, the people who actually make the battery, they say the battery is rated at 30 C. They give you that definition. It is rated at 30 C. Then the battery has been specified to put out 30 times its amp hour rating. So it will put out 3,000 amps. And if it's rated at 30 C, it should then do it for 2 minutes. If it's rated at that. If it says it can do that continuously, then it should be able to do it for 2 minutes, okay, in this calculation. So moving on, 20 C, 10 C, 5 C, 1 C, which is also the same thing as saying C1, just so you know. But as that number is on the left-hand side of the C, see, it's a prefix, 30 C, 20 C, 10 C, 5 C, 1 C, right? Then after that it becomes a suffix, a prefix and a suffix, but I'll explain that in a second. So let's say it's 10 C. So now we're saying 10 times the amp hour rating. So 10 times 100 would be 1,000 amp draw, let's say, and then we're saying that 60 minutes or 1 hour divided by 10. So in one case, in one part of the equation, we're going to be multiplying the amperage. In the other part of the equation, we're dividing the minutes, or 1 hour is 60 minutes divided by 10. So there we're saying that a 100 amp hour battery can do 1,000 amp draw for 6 minutes. Okay, and that works out to 1,000 amp draw for 6 minutes works out to mathematically 100 amp hour, 100 amps for 1 hour. But that's if the manufacturer has specified 10C continuous. If it has specified that. Now we're going to get into that in just a minute, to where if they specify a different number and you say, well, okay, if it does this, then it must be able to do that. That's not the case, right? That's not the case. I'm going to explain that in a minute. And this is, like I said, manufacturer specified. All right, so for example, we'll get down here. Let's go down to 1C. 1C would be 100 amps for 60 minutes divided by 1 is 1 hour. So whether you say 1C or C1, the rating's the same. 100 amp draw for 1 hour. Whether it was written as 1C or C1, it would be the same thing. They're both accurate. It can be written either way. Okay, so just know that 1C or C1, that's the same exact thing. Okay, and I would state that with the factor of 100 amps for 1 hour. Okay, but let's move on down. So let's get down to 0.5C, 2.2C, 0.1C, 0.05C. Okay, so here's what you gotta know. So 0.5C, right, which is the same thing as saying C divided by 2, and in most cases you'll see that they drop the division mark and it'll just say C2. Okay, so but I wrote it in here. I put it in here on purpose so that you understand that like C20 would be C divided by 20. Okay, that's why I want you to know that, right? Okay. So in this case, we got, let's say, 0.5C. So that would mean that 100 amps divided by 2, right, 0.5, would be a 50 amp draw. So C divided by 2, or the 100 amp, the value divided by 2 is 50 amp draw. Or if you took 0.5C times 100, 0.5 times 100 is 50. So either way, 0.5C or C2 gives you the same value. But at this point, now we're going to take that same value, instead of up here, we were dividing 60 minutes by 30. Now, since that is no longer a prefix, we're now using it as a suffix, as example, right? So it's a suffix comes after it, right? So now we're going to say 1 hour times 2. So in this case, 0.5C is going to be 100 times 0.5 or 50, or 100 divided by 2. But at the same time, if it's a C, that would then be C2. That'd be 1 hour times 2. So think about it like this. If it's a 100 amp hour battery, you can do 100 amps for 1 hour. 100 times 1 is 100. Okay, a C2 rating is going to be 50 amps for 2 hours. So 50 times 2 is 100. So we still have a 100 amp hour battery, right? It's just rated differently, right? Let's say the manufacturer says it's a C2 rating. So they provide you with a rating of C2. What they're saying is that battery was able to provide 50 amps for 2 hours nonstop, right? It can do it. That's what they're saying. And that's how they came up with their 100 amp hour rating, right? Now, in most cases, if you have a lead acid battery in particular, it's going to be a C20 rating. It's very common. Sometimes C10, sometimes both. Sometimes they'll give you both, which is interesting, which is good. It tells you a lot about the battery. But, and we'll get into that in a minute. Like I said, I got to explain that a little further. So let's say it has a C20 rating. In most cases, if you're going to go buy a lead acid battery, right, and on the battery it just has AH, amp hour. Nothing else is written on the battery. Doesn't say C20, doesn't say C10, doesn't say anything. Just AH. You can pretty much bet if it's a lead acid battery, then it's been rated at C20. Okay? Unless it states differently. And sometimes in order to know that, for sure, you actually have to go to the manufacturer's literature for that battery. It may not be on a label, but you can go to the literature. The literature also doesn't state C20 or C10. It just says amp hour. Then it was rated at C20. You can pretty much bet on it. Now, same situation, 100 amp hour battery, rated at C20. Now, you would tend to think to yourself, if you didn't know any better, you say, well, okay, it's 100 amp hour. That means it can do 100 amps for 1 hour. Makes sense, right? It's perfect math. 100 times 1 is 100. So it must be able to do it, right? It can't do it, right? It won't be able to do it. If it's actually rated at C20, you won't get anywhere near that. The reality of it is that at C20 rate, which is going to be 5 amp draw for 20 hours, so like we said, 0.05C is the same thing as C20, right? 1 divided by 20 is 0.05. That's where I come up with that. So 0.05C, or 0.05 times the capacity, C, would be 100 times 0.05, or 5. Same thing, if you took 100 divided by 20, you'll get 5. Right? It's the same thing, whether you divide it or you multiply it. Okay, but then we're going to be saying that the 20 factor is going to be actually 1 hour times 20. So now we're saying 5 amps for 20 hours. So 5 times 20 is 100, or 100 amp hours, right? That's how they come up with that rating. Which is not, they are not saying to you it can do 100 amps for 1 hour, which is a much greater rate of discharge for a much shorter duration. But if you didn't know any better, you would think, yeah, it can do it. It can do 5 amps for 20 hours. Why can't it do 100 amps for 1 hour? Well, it can't, right? And there's a reason for that, and that's Peukert's law, and we're going to get into that, okay? So this is what C ratings are all about. Now, I made some notations down here. So what I want you to know is that in most cases, when a battery is rated, the prefix, like for example, if they say 10C, 5C, it's greater than 1C, 5, 10, 20, 30. They're usually talking about your maximum safe discharge rate or your maximum continuous discharge rate. But in some cases, in your lithium ion based batteries, when you get, usually when the battery is recharging, usually it's not at 5C continuous, but some of them are. Some of them are at 5C continuous, some of them are even higher than that. And that can be really a problem, a real problem when it comes to recharging a battery with your alternator. Okay? So for example, let's say that the recharge rate of a particular battery that you're looking into has a recharge rate of 5C continuous. And it's a 40 amp hour battery. That means that that battery can accept 40 times 5 or 200 amps of charging current. That's its C rate for charging is let's say 5, and it's a 40 amp hour battery. It can accept 200 amps non-stop. The battery can do it, won't damage the battery, it'll recharge it very rapidly. But your alternator was not going to be able to put out 200 amps non-stop without damaging the alternator. It's going to overheat. It may not be designed for it at all. Maybe even the cables coming from the alternator itself are too small. Who knows, right? It just can't do it. And it's something you need to be aware of, and something you need to make a decision before you purchase that battery on how you're going to charge it. Yeah, it can recharge really fast, but so fast that it could damage the alternator in your vehicle. So it's something you got to be aware of, right? So, for example, in most cases, like on a lead acid battery, something in the order of like 0.1C to 0.5C. So, for example, let's say it's a 100 amp hour battery, somewhere between 10 amp hours and 50 amp hours, and 50 would be on the high side, would be the max that the battery manufacturer would recommend. And the alternator itself can usually handle between 10 and 50 amps nonstop, without damaging the alternator. It can easily do that. So the alternator in a vehicle is designed for a lead acid type battery, whether it be a GM or a standard flooded lead acid battery, whatever it might be. It was designed for that. Not necessarily designed for the lithium ion battery you plan on sticking in there. And something you got to be very aware of, and something you need to check into. Okay. So usually when the number is greater than 5 or greater, we're talking about the rate of discharge, like how rapidly and for how long it can discharge the battery. Not only continuously, but maybe even for just a pulse for 3 seconds or 5 seconds. That would be its C rating, and usually it would be a prefix of 5 or greater. When it gets down to 1C or less, usually at that point we're talking about an actual not a charge rate. So let me tell you what I've got wrote down here. So let's say, for example, 100C down to 5C is going to be your maximum safe discharge rating in most cases. Okay, 1C or C1 is a battery's amp hour rating. Usually if you see 1C, they're talking about the actual amp hour rating, and usually that's in a lithium ion based battery. Below that, let's say 0.5C all the way down to 0.05C or C2 down to C20. Now we're talking about a specified discharge and recharge rating, and that is more common. But like I said, this is just a notation. It's not set in stone. But I want you to understand a C rating. It has to do with its discharge rate and its recharge rate, and what the manufacturer rates it at. And that does not mean, like I said before, that you can come in and just change that from, let's say they rated it at 0.05C, and you say, okay, well then, obviously if I do the math at 1C, it can do this. Well, no, it can't. Like I said, in a lot of cases for example, a lead acid based battery, if it can do, let's say 100 amps at C20 at a 5 amp rate for 20 hours, total of 100 amps or 100 amp hour, if you were to do it at a C1 rate, you said, you know what, I'm just going to go do that at 100 amps and see how long it lasts. It should be able to last an hour. It won't. It'll be more like 36 minutes. Something along the lines of like 60% of an hour. So much less. So at that point, if it can do 100 amps for 36 minutes, 60% of an hour or 0.6, that'd be a 60 amp hour rating at C1. So you went from 100 amps to C20. Now all of a sudden you're testing it, and now it's coming out at 60 amp hours. Like, something's seriously wrong. Well, it's not anything wrong. It's just it has to do with the battery chemistry and Peukert's law. Like I said, we'll get into that. And how it's affected by the rate of discharge. So your C rating is not necessarily fixed. It is specified by the manufacturer, and something that you have to go by. It's something that you need to look up, and something you need to record. And when you're making a decision about one battery or another, and you're looking into power density, you have to understand that the different C rates will greatly affect your actual power density. So it's not just the energy density. It's not just a C rating, it's a combination of the two to give you your power density. All right, then, so let's move on and talk about Peukert's law, aka or also known as the Peukert effect. All right, and so what does that mean? Let me define that real quick. A battery's capacity rating decreases as its discharge rate increases. Let me say that again. So Peukert's law, or also known as the Peukert effect, is defined as a battery's capacity rating decreases as its discharge rate increases. So that's going to go on to explain how if a C rate is 20 hours, C20, right? Very low amperage, let's say 5 amps for 20 hours. So its rate's very low, and we got 100 amp hours out of it. But as we increase the rate to C1, and we said we're going to do 100 amps, right? So the capacity rating, so the discharge rate increased from 5 amps to 100 amps. The capacity rate decreased, right? Like I said, so for example, instead of getting 100 amps at 100 amp hour capacity at C20, we went to C1. Instead of discharging it in 20 hours, we discharge it in 1 hour. Instead of getting 100 amp hours, we got 60 amp hours, or roughly 60%, which is close. 58 to 62% is usually what you'll see in a lead acid battery configuration. So, like I said, a battery's capacity rating decreases, the rating decreases, the amp hour rating goes down as we increase the discharge rate from, let's say, 5 amps to 10 amps, 20 amps, 50 amps, 100 amps, 200 amps. As we increase the discharge rate, the capacity rating is going to go down, right? That is Peukert's law, also known as the Peukert effect. Now, that is due to the battery's internal resistance and electrochemical limitations. Now, I separated the two. I could just have said to you that is due to its internal resistance, the battery's internal resistance, and dropped it. Because, in all honesty, electrochemical limitations are under the heading of internal resistance. But I want to separate the two. I want to actually talk about internal resistance and electrochemical limitations separately, and then we'll combine them together as like the overall resistance. Okay, but we need to break them down so that it's more understandable. So, battery's internal resistance, 3 types. You have your ohmic resistance, okay, which is your measured resistance value. Same way if you were to take an ohm meter and check the continuity of a wire from one end to the other and you get an ohm value, you know, a resistance value. Same thing. If you were to check the resistance through a battery from one post to the other, right, through the posts, through the electrolyte, right, through the plates, through the cell connectors, right, that total resistance is your ohmic resistance, which is a measured value, right, your measured ohmic resistance. That's easy to understand, and that's where I said internal resistance, that's what I was talking about. Now, let's move on to electrochemical limitations, and that is the other 2 types of internal resistance. That is your reaction resistance, which is your chemical reaction charge transfer resistance. Okay? Okay. And then from there, we're talking about diffusion resistance. That is the charged ion transport resistance. Okay? All right? So this is the electrochemical reaction process we were talking about, right? And the chemical reaction process, when I say charge transfer resistance, that is between the electrolyte and the lead plates, right? Whether it be lead dioxide or your sponge lead plates, and the electrons and the positively and negatively charged ions from the electrolyte, the transfer from the electrolyte to the plates, and when you're discharging and then when you're recharging, vice versa, right? It goes in reverse. So your chemical reaction charge transfer resistance. Then we got your diffusion resistance. One's known as reaction resistance, right? That's chemical reaction process. Then we've got diffusion resistance, which is your charged ion transport resistance. Now think about it like this. Let's say that the electrolyte, okay, let's try to exaggerate to make it easy for you to understand. So you have your positive plate and you have your negative plate. Between the 2 plates, you have a separator. All right, now in an absorbed glass mat battery, that separator is like a fiberglass mat, and the electrolyte is absorbed into it. It is then sandwiched between 2 plates. So here's a plate, here's an absorbed glass mat with the electrolyte, and they're sandwiched together nice and tight. Let's say for ease of understanding, or to drive this point home a little bit, let's change it up a little bit. Let's say it's not an AGM battery. Let's say it's a standard flooded lead acid battery, and in between the 2 plates you have a separator. That separator is not an absorbed glass mat. So the electrolyte's a liquid solution. And that separator is porous, so that the electrolyte can pass through it. Right? It's porous, you know, like a sponge, let's say. And the electrolyte can pass through that separator from one plate to the next or back and forth, right? Through the separator. Now let's just make it easier to understand. Let's put those plates really far apart. It's not like this, but it'll be easy of understanding. Let's put that separator in the middle. Let's put the electrolyte out of here. let's say the electrolyte, the charged positive and negative ions in the electrolyte has to pass through the electrolyte, let's just say, through the separator and over to the negative plate. And then it has to pass through the separator and over to the positive plate. Well, there's a time factor involved. That takes time. And for example, if we exaggerate it more, you can see that time factor increases. Now, AgM, the electrolytes suspended, right, in the glass mat separator, and they're sandwiched together, so the amount of time to travel from one to the other would be very low. Whereas if it's a flooded lead acid battery with a porous separator, now the distance or the time becomes greater, right? Kind of makes sense, right? So that is actually called diffusion resistance or charged ion transport resistance. Like we're like hauling it from one plate to the next. You know, get in the back, let's go. I'm gonna drop you off over here. Get in the back, let's go. I'm gonna drop you off over here, right? That's diffusion resistance. Now we've actually delivered it. We've dropped it off. Here you are. Here's your stuff. Here's everything you need. I'm gonna go ahead and deposit all this electrolyte on the surface of your plate. Then the chemical reaction process takes place, and that takes time also. So that's your reaction resistance, your charge transfer resistance. Now that we've delivered it, right, we've then delivered it to the plates. You know, here's what you need for the chemical reaction to take place. Now the chemical reaction has to take place, right? Okay, that's your reaction resistance, and that's your diffusion resistance. So between the three of them, ohmic resistance, reaction resistance, and diffusion resistance, that is a battery's internal resistance. So the ohmic resistance is a given, right? As the battery temperature changes, gets colder and hotter, it changes to some degree. Okay, but the reaction resistance and diffusion resistance, right, that, like I said before, that's a time factor. So let's say that we have a battery, it's fully charged, okay? It's fully charged, and we said it has a lot of stored energy, but that's not all the battery can offer. We still need for that chemical reaction process to be ongoing as we discharge it. But as we're stating, well, that takes time, okay? So if we discharge that battery at a faster rate than the chemical reaction, diffusion resistance, or the transport process and the charge transfer, the chemical reaction process and the transport process, if we discharge it at a rate greater than that can occur, right, then the capacity of the battery goes down. Not because of its initial stored charge, but because of the available electrical energy. We're removing it quicker than it can replenish it. Right? Simple as that. You know, for example, if you have a swimming pool and you put a hole in the side of the pool this big, right? And you put a hose, a garden hose this big, and you're putting water in, but you're taking water out at this rate, right? It's got a lot of stored capacity, a lot of stored water, but you're depleting it faster than you can replenish it. So its total capacity is going to be less than if we were to deplete it slowly, right? So imagine we depleted it slow. So now the actual opening in the side of the pool is smaller than the hose feeding it, and we're removing it at a slower rate. Okay. So now, right, the hose can replenish what we're taking out faster. It can replenish it just as fast, if not faster, than we're taking it out. Right. So it's a rate of discharge in relation to the rate of the electrochemical reaction process. Now let me move on a little bit further. I think that kind of drives that point home a little bit. So electrochemical limitations, let's get in that a little further. This is exactly what I'm talking about. Relates to the rate at which the electrochemical reaction process converts chemical energy into electrical energy, right? And that is your reaction resistance and your diffusion resistance. The electrical current production rate restriction factors, right? So basically, like as the battery is producing electrical current, right, it's doing it at a given rate, okay? And if we are depleting or discharging that battery at a rate greater than that, then it can't keep up. Okay, so here's the thing about this. Okay, so that is your electrochemical limitations. That is the three internal resistances, right? Your ohmic resistance, reaction resistance, diffusion resistance, and this is all about Peukert's law and the Peukert effect. Now, here's where lithium-ion batteries have the advantage. They are affected by this in a very minor way, and in some tests I've seen, not at all. Right, so now we move forward and we say, okay, well, like how, you know, so how do you determine, you know, how much of an effect this is playing on the particular battery that you're going to purchase? You know, does it have a big effect? Does it have a little effect? Does it have no effect? If it has no effect, well, that'd be great, right? But if it has a little effect, well, that's better than a big effect. You know, let's say, for example, that it's a 100 amp hour battery, but if we discharge it at 100 amps, instead of getting 60 amp hours, 100 amp hours, instead of getting 100 amp hours, so at 100 amp hours at C20 rate, That's what it's rated at by the manufacturer. We discharge it at 1C or C1. We get 60 amp hour. Well, let's say that the battery gives us 80 amp hour, this battery, and this other battery gives us 50 amp hours. Okay, well, one is obviously can deliver electrical energy at a greater rate than the other, right? So you got to be able to compare them. All right, so how do you compare them? That is known as the Peukert's law exponent, also known as the Peukert's constant. Now, so what I'm going to give you here is not a calculated value. I'm going to give you a range that could be assigned to the equation that can be performed to determine one battery, to compare one battery to another. You can perform an equation to determine the effect of the Peukert's law or the Peukert effect. You can perform equations, but you need to know the Peukert's constant, or also known as Peukert's law exponent. You need to know that value. So what I'm going to do is, and this is for just for well, what am I trying to say here? Something, so you'll have something to go by, right? A range, if you will. You know, not the exact Peukert's constant for the exact battery that you want to purchase, but what is a general range so that you understand one battery to another. All right, so my first one here I've got, and I said, so here I'm just going to define it real quick. An assigned calculation value, an assigned, okay, not calculated value, but an assigned value. An assigned calculation value given to a particular battery type or chemistry, right? So for that reason, you can actually look up, like, what is a range? You know, what would be a specified range of Peukert's constant or Peukert's law exponent for this particular battery, right? That being said, lithium-ion batteries are going to be listed somewhere between 1.02 and 1.05, so an average would be 1.035. That would be the constant you would use in the equation. Let's say it was 1.00, that would mean it would have no effect, that the battery is totally unaffected by this and Peukert's law does not even apply, right, if it was 1.00. Now here's what you got to know. Some testing shows that what I've got here is accurate, 1.02 to 1.05. It has a small effect, but not a very big effect, a very small impact. Lithium-ion technology is such that it doesn't suffer from that nearly as much as lead-acid batteries, which is a big plus. One of the big performance benefits of lithium-ion batteries is that they are not really affected by this, or by very little. But some testing has shown that it's not affected by it at all. As a matter of fact, so let's say 1.00. But in some testing, to even elaborate on that further, some testing has actually shown that as you increase the rate of discharge, the battery itself, the electrolyte in the battery itself, the plates, they heat up. And as they heat up, the efficiency gets better. So instead of it being affected not at all, it actually improves. So instead of it being, let's say, just as an example, let's say it's a 100 amp hour battery and we tested at C1, we get 100 amp hours. We tested at C2 or C20, so we get 5 amps for 20 hours, 100 amp hour. C1, 100 amp hours, 100 amps for an hour. But now we ramp it up. We do 10C, so we do 1,000 amps, right? Okay, well, 1,000 amps, you know, to be a 100 amp hour battery would be 1,000 amps would last for 6 minutes. So 1,000 amps for 6 minutes is 100 amp hour. If you do the calculation, right, that's 100 amp hours. So 1,000 amps for 6 minutes would be a 100 amp hour battery. But instead of going 6 minutes, it goes 6.5, 7. It's actually greater, not less. So that's actually, it's not only is it not affected, but heck, it actually gets better the more you discharge it, actually, as the rate increases. So there's some speculation or some discussion or what else can I say? Some argument, maybe you might say, as to whether this is accurate. Should it be 1.00? Should it be 1.035? Should it be 0.98? You know, just think about it like this: lithium-ion batteries, lithium ferrophosphate, lithium titanate batteries, they are almost not impacted or not at all, right? So it's not really a thing for them. All right. So that being said, let's move on to your lead-acid batteries. So which one is impacted the least? That's your AGM batteries. Your sealed lead acid, also your valve-regulated lead-acid batteries. They are least impacted. Okay. And that goes back to what I was saying about the separator plate being absorbed glass mat. The electrolyte is suspended. It's sandwiched between the plates. It goes back to diffusion resistance. Not so much reaction resistance, but to some extent but the fusion resistance. It's a more efficient battery, so therefore it's on average 1.10, let's say. So it is affected. It's not 1.00 by any means, but it is about 1.10. And a gel type battery is also a sealed lead acid, valve regulated lead acid battery. It's going to be somewhere around 1.175. And then your flooded lead acid standard batteries, just your standard vented flooded lead acid batteries, are going to be somewhere around 1.40. So they are affected the most. So Peukert's law most certainly is going to affect the battery's capacity rating, especially in a way that as the C rate increases, the amp hour rating of the battery capacity decreases, right? And then there's one other thing to talk about is when I talked about earlier was voltage sag or voltage dip. All right, so different batteries, as the battery is discharging, it's called the discharge curve, right? As the battery is discharging, how does the voltage curve look? Right, so for example, if we're discharging a battery, it's a 20 amp hour battery, and we discharge it for 20 amps, and after 1 hour, it tanks, right? Battery's done. So let's say we discharge it at, instead of 20 amps, we discharge it at 80 amps. So how much does the voltage drop? And what does that voltage curve look like? Okay, another benefit from, another in the plus column or the pro column for lithium ion batteries, lithium ferrophosphate, lithium titanate batteries, compared to lead acid batteries. And like I said, it does matter whether it's an AGM or a gel or an FLA battery, standard FLA battery. It does matter because they're not all the same. Is that the voltage curve as you increase the load on the battery, right? So for example, if you have a lead acid, an AGM type battery, and you're discharging it at a very low rate, let's say 5 amps over 20 hours, right? The voltage curve is going to be fairly flat. It's going to taper off gradually, but let's ramp it up. Let's do it, 10C, 1,000 amps. Now the voltage curve starts to have a very downward slope. So as it's discharging, the voltage is dropping as it's discharging, right? So basically, not only is Peukert's law affecting the overall capacity rating of the battery, as we discharge it at a higher rate, the voltage itself tends to drop as we discharge it, okay? So that is voltage sag, voltage dip, or voltage drop while being discharged, and that kind of explains the differences between lithium ion based batteries and lead acid based batteries. Okay, so what I have here on the board is going to allow me to illustrate how a battery's capacity rating is greatly affected by its discharge rate, and how a battery's energy density and power density are greatly affected by its temperature. Now on the board here, what I have is two different lists of specifications, both by the same manufacturer for two different batteries. These are both Odyssey batteries, though they're AGM thin plate pure lead batteries, and here's the actual part numbers, ODX AGM 31s and ODX AGM 24F. Okay, and this is what is listed in their specification sheet. And I want to show you that here's your pulsed hot cranking amps, cold cranking amps, also known as marine cranking amps, hot cranking amps, C20 rate, your C10 rate, your reserve capacity rating, and I'm going to break down exactly how they change, right, and what affects it. Same thing over here, same list of ratings, different battery. So at a 5-second pulsed hot rating, that is at 25 degrees C, 77 degrees Fahrenheit. Once again, pulsed hot cranking amps can also be written as pulse cranking amps in most cases. Pulse cranking amps and pulse hot cranking amps are both rated at 25 degrees C or 77 degrees Fahrenheit, which means they're basically exactly the same thing. Not basically, they are, right? Okay, so as the battery temperature changes, you see that their rating for this battery is 1150 amps at 0 degrees Fahrenheit and negative 17.8 degrees Celsius. But the rating goes up when it goes to 0 degrees Celsius, 32 degrees Fahrenheit, so there's a big jump. And we're going to go from 0 degrees C to 25 degrees C, 77 degrees Fahrenheit, and we're going to jump again from 1370 to 1545. So as you can see, the rating on the battery changes drastically. And as far as a battery's C rate or its C rating, you can see that here's hot cranking amps, here's pulsed hot cranking amps. Now this is going to be for a specified duration. This is for 5 seconds, right, as opposed to 30 seconds, right? So 30 seconds or 5 seconds. So you can see at a 5-second rate, the rating is much higher than at a 30-second rate, right? So same situation over here, same exact scenario, pulsed hot cranking amps or pulse cranking amps, cold cranking amps, marine cranking amps, hot cranking amps. As you can see that as the temperature goes up, right, or as it goes, or you can say it the other way, right, as the temperature goes down, the rating gets less, or as the temperature goes up, the rating goes up. So the battery has the ability, it has a greater energy density or greater power density at 77 degrees Fahrenheit than it does at 32 degrees Fahrenheit or 0 degrees C or 0 degrees Fahrenheit, negative 17.8 degrees C. So as you can see, greatly affected by its temperature, okay? So as the temperature gets colder, the rating goes down, right? Its actual available energy or maximum C rate or power density goes down. Okay, so let's rate the battery. Let's look at its capacity at different discharge rates. So this battery is rated at 103 amp hours at C20 rate. It's rated at 98 amp hours at a C10 rate. And its reserve capacity is 220 minutes. Now reserve capacity is 25 amp discharged across the board. Everything with reserve capacity was done at 25 amps and for a given amount of time. So in this case, it was able to do 25 amps for 3.666 hours, right? So if we break this down further, we know that at a C20 rate, we were able to do 5.15 amps for 20 hours for a total of 103, right? 5.15 times 20. A C10 rate, we were able to get 98 amp hours or 9.8 for 10 hours. So if this was the same as that would actually be 10.3 times 100 would be 103. But as you can see, as we increased the rate, the duration became less, so it dropped. So as the rate increased, the battery capacity decreased. Peukert's law, right? So same scenario, we can calculate an amp hour rating from the reserve capacity. Since we know it's a fixed rating of 25 amp discharge, we know that we know it went 220 minutes, we can take 25 amps times 220 minutes or 3.666 hours and find out that at a 25 amp rate, we actually have a 91.67 amp hour battery. So 103, 98, and then of course 91.67. So as the rate of discharge increases, you can see the amp hour capacity is going down. Like I said before, Peukert's law, right? The Peukert effect. That illustrates it right there. Same scenario over here, same exact consequence, right? As the rate goes up, right, as you discharge the battery at a greater rate, its amp hour capacity goes down, 76, 73, all the way down to 66.67. And as you keep going, you'll see that the actual amp hour rating goes down, down, down. It keeps going down as you discharge at a higher and higher rate. So this is from the battery manufacturer. This is their specifications at different temperature ratings and at different discharge rates. So this illustrates exactly what I'm talking about, how temperature plays a big influence and how the discharge rate also plays a big influence, right? Okay, so one thing I do want to mention to you is that the lithium ion battery chemistries, lithium ferrophosphate, lithium iron phosphate, lithium titanate, lithium titanium oxide, they are much less impacted with the discharge rate. Right? Like I said, the Peukert effect is not such a big issue. For example, if it was rated at, let's just say, this is an example, 100 amp hours, and you said, well, that's at C20, well, then it would be, like at 100 amp hours, it would be 5 amps for 20 hours for 100 amp hours. If you then said, well, let's do it at 10, as C10 rate, it would then probably be very close to 10 amps for 10 hours or 100 amp hours. It's not affected as much. You know, like I said, in some cases, actually, it can get better as you discharge at a greater rate. So this is more lead-acid battery related, and why one of the big advantages, or one of the biggest advantages in switching over to a lithium-ion based battery from a lead-acid battery is the performance, and it has to do with Peukert's law or the Peukert effect, and that's what I want to basically illustrate. And like I said, this is from the actual battery manufacturer's website. This is their battery. This is their ratings. Not something I made up or some numbers I'm just pulling out of my butt, right? This is reality, and this is for a lead-acid AGM thin plate pure lead, top of the line AGM type battery, and these are very, very capable batteries. I didn't pick, you know, some of those small, you know, low capacity batteries. These are high capacity batteries, and they do perform very, very well. But the lithium ion batteries do have an advantage in that way, right? Okay, to wrap it up, if you found this or any of my content worthwhile, please take a few moments to comment. And if you happen to know someone that may find this content useful, please take a moment to share this channel with them. Thank you all for that. I'll leave you with one final thought. Let's all try to remember to give thanks, to remain humble, and to show a little kindness. It certainly can't help. It certainly can't hurt, and who knows, it may actually help. Thanks for your time, and I hope to see you on the next one.